Hello. Can you hear me or see me? Hello. 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 I can hear you, but I think there is a bit of echo from your side. Can you see me and hear me? You can see me. All right. All right. So I'm all set. There is a considerable echo from your side. I think you have two microphones on, and your microphone is picking up your speaker or something like that. Hello, can you hear me? Or see me now? My camera is on. All right. All right. Very nice. I mean, unfortunately, I can't see you, but going by the size of the clap, it looks like I have a big audience. So, first of all, an apology from my side that I could not come physically because I'm still recovering from recent illness and I could not undertake the journey. The doctor did not allow that. But leaving that aside, I think we can have a good discussion on what we, uh, what I communicated to Muktisa earlier, that we can discuss a little bit on open quantum systems, its early days, and how we deal with open quantum systems, and some recent results, some recent developments. So that would be the focus of the talk. The talk will have two parts. The one part would be like a board work where I will try to do things just like we do it in the class. So on the board, I'll try to explain slowly what's happening. And the other part would be a recent development in our lab. And we are working on open quantum system for quite some time. So that part I would like to show you through the slide. I will begin with slide and then switch to board work and then come back to slide. Okay. So I would like to begin and thank you very much, everyone, particularly Muktisa and Shomadip, who communicated to me about your program. So thank you very much for the invitation. I would like to start now. I'll switch on my camera. And your questions, if you have, you may have, it would be nice if you can send those questions through chat box. I know it might be somewhat problematic because you have a big audience, but still, please give it a try. It will be very helpful. Now I'll switch up the camera and start sharing my slide. Please confirm that you can see the slide. Yes, okay, thanks. Great. Right. So, the topic of today's talk is basically closely connected to your broad topic, quantum optics and light, in a way that we are going to look at open quantum systems. Open quantum systems are a class of quantum systems where, not exactly class of quantum systems, it's quantum systems which are connected to harmonic reservoir, or rather, how do I say, it's connected to the surrounding, to the environment. Such systems, they have slightly different behavior than what you expect from the Schrodinger equation. So today's talk will be exclusively on open quantum systems. I'd like to just start from very basic so that, I was told that I do have some undergrad and postgrad students there. So, I'll try to make the argument simple enough so that all of you can pick it up and understand exactly what's going on. Before I start, I would like to show a little bit of my research group in lab. We work on open quantum systems. Specifically, we look at the non-equilibrium dynamics of the system, and we develop quantum master equation and similar equation which can describe open quantum systems. And we have
we are working on applications like quantum computation, quantum optics, foundations of quantum mechanics, quantum technology, spectroscopy, then thermalization problems, and then transport. And some of my students who are recently very active are always on Chakravarti, Autumn, Nilanjana, and Shapurshi. So, I mean, the entire work, the major volume has been contributed by them. Now, we go back to the basics. What are the open quantum systems? What are open quantum systems and how do we deal with them? And what was the early developments? To take a look at that, and at this stage, I would like to switch to the board work. In this sense, I will stop sharing this slide and I will start sharing my whiteboard. Okay. So if we will confirm that you can see this green screen that I see here. Oh, very nice. So I would like to begin with something that we are quite familiar with. How does a physical system evolve with time? For example, I mean, let's look at a very simple example that we all know very well. Suppose we throw a projectile, it follows a parabolic geometry. This is one of the classic examples. We have been studying this probability from our class 2. And the dynamics, the description that we throw the projectile of certain mass at an angle with some initial velocity and that it follows a parabolic trajectory, it is given by a set of laws. And these laws, I mean, particularly this is, we are referring to Newton's laws, the first law and second law. They define how the trajectory will pan out. It will be a parabola. And we get this from Newton's law. So Newton's law, the mass times the acceleration is equal to the externally applied force. This essentially tells us that for a point particle, which was, initially suppose it is at a particular position, or how does R change with time? This is the essentially dynamics of a physical system. So interestingly, this dynamic Newton's law, it is reversible. Reversible in the sense, suppose initially the particle was at position R1 and it has evolved over time to another position R2. Now, if you know the initial velocity and the position, then using this second law, you will be able to figure out after certain time, after the time duration delta t, where exactly the system will be at this point. You will be able to figure out R2 exactly. Similarly, if the system is at R2 and you are given the velocity at that point R2 and the position, meaning the value of R2 itself, you can use this equation to backtrack the evolution of the particle. You can come back and find out from where it started. So which means that the trajectory is unique starting from any one point. You will be able to completely predict the future points. So the dynamics is completely deterministic. And given any point, you can go back in time using this equation or forward in time. So you have no restriction whatsoever. This is reversible deterministic dynamics. This is Newton's law. Now, in quantum mechanics, we have exactly the similar situation, except for a point particle in classical systems, we use Cartesian coordinates. For quantum mechanics, we are familiar with it. I guess that oftentimes we designate the state of the quantum system by a wave function psi, and it's corresponding shape form, which I'm not explaining, I'm assuming it is the shape type is familiar to all. It is basically a point in the Hilbert space. So what I show you this box is basically Hilbert space and quantum system at a particular time, a particular quantum system at a particular time can be designated by shape type, let's say. Now, Schrodinger equation, which is it tells us, I mean, I have written it in regular form, but it tells us that how in the Hilbert space a quantum system evolves. So starting from psi, it can go to another point outside. So if initially the system was having, I mean, system had a particular bit form, a function, and if you make it evolve under a particular Hamiltonian, a quantum system goes from one point to another. It's very similar to a particle going from one point to another in Cartesian space using Newton's law. Or if you would like to be more careful, then you would say maybe a better analogy would be a phase space description instead of Cartesian coordinates, a general phase space description of a physical system which starts from one point and using Newton's law you will be able to find out that this system goes to a classical system goes to another point. And then again these trajectories are usually completely deterministic and reversible if there is no dissipation, of course. And in quantum systems again, Hilbert states the evolution given by solidification assumes no dissipation. So in such cases also, if you have complete knowledge of initial conditions, then the dynamics is deterministic. You will find type exactly on the related. So that is all very good. It means this is deterministic, reversible again. You can go back, you can go forward, no restriction whatsoever. The problem is the real life, as you see when we do experiments, we do not see reversibility that easily. What we see is entropy is always increasing and we always encounter dissipation, and what we get is to start from a particular point, the system evolves, goes to another point, but oftentimes if we have a particular system at a particular stage, we cannot backtrack and predict what from where did it come. So for example, let's look at a classical example of what I was telling you. This is what I was telling you in the classical case. This is Newton's law. No dissipation. But suppose there is dissipation, then what happens? Let's take a classic case of a harmonic oscillator. This is a harmonic oscillator. Suppose the pendulum oscillating, its space for small angle oscillation will be a closed bed. But if there is dissipation, then we know it will spiral and eventually it will stop. It means the center point. That's very nice. So irrespective of where we were initially, if we let it evolve in the presence of dissipation, then the pendulum, all pendulum will stop and eventually everything will have Q and P both will be zero. Now, suppose you do this experiment, or rather think of it, I give you a pendulum which is stop, meaning I give you something at this point here, and I ask the question, can you predict where did it come from, meaning exactly how it was oscillating before? That is impossible. You say, you can't say that because this is the point where many of the physics trajectories converge. This is a distributed system. In a non-distributed system, they don't intersect. But this is a distributed system where many physics trajectories converge at zero point, so it is impossible. It is a classic example of irreversible dynamics. If the system system is already in equilibrium, then we do not know where it came from. We can look at a glass of water, but we cannot really predict whether that glass of water it came because there was some ice inside the glass which melted and formed the water, or there was water vapor which basically condensed and gave into water. It is not possible to say. So this is a hallmark of irreversible dynamics. And this irreversible dynamics is manifested everywhere. Classically, we have some way of dealing with it, Newton's law and the anticipation. But the problem is, what do you do with quantum systems? So this is where the concept of open quantum systems comes in. Schrodinger equation cannot give you that information. Schrodinger equation is irreversible. So, where is the source of irreversibility? In quantum systems, there are two sources. One is measurement, and second is contact with the environment. Let me explain quickly what are these. Let's suppose, again, we consider a Hilbert space. Initially, the system was in some state psi, and suppose you do a measurement. You measure an observable wave whose eigenstates are phi 1, phi 2, phi 3, and with corresponding eigenvalue lambda 1, lambda 2, lambda 5. So suppose you measure this observable wave on sky. What is the outcome? You say we know that. It's simple. The system will collapse to either this wave function, its probability P1 that P1 is given by or it might collapse to phi 2, its probability P2, or it will collapse to phi 3, probability P3. Okay. So once a measurement takes place, a quantum system goes from a pure state to a mixed state, and because it has different probability to be in different states. This is one-to-many journey. Of course, we do not have any analytical description per se. So that means we do not know how the trajectory looks like, but we know the initial point and the final point. This initial point is known, and the final points are also known. This one-to-many journey is basically a signature of irreversibility. Because you cannot do that. Suppose you are here. It is impossible to say whether you started from psi or some other psi prime. We do not simply have any mathematical tool to go back. So which means the measurement is a convenient tool to give you a kind of sense of irreversibility. The other one is the contact with the environment. This is what I'm going to talk about. Contact with the environment in what sense? In the same sense as the measurement, that if the system was in a particular state, and if it is connected to the environment, what happens is after evolution, a certain amount of evolution, the system has different probability to be in different states. It means the final base station is mixed. So this pure state to mixed state, whenever such a journey takes place, what we have is we have increase of entropy. Entropy increasing is very good, that is the reversibility, and this is what we are trying to do. So essentially, open quantum systems help us describe such processes. Now, because I can't see you, oftentimes what happens when I see you, I look at your face and I have an immediate idea that whether you're following me or not. I would like to give a pause for 1 or 2 minutes and would like to invite questions. And if you have questions at this stage, please speak to. I think it would be better that if you have questions, feel free to type in the chat box or just ask the question at any time during the talk. And in that case, I will slowly proceed to the next part. Now, one of the early detections, one of the earliest stage where we had the open quantum systems came into serious consideration was when nuclear scenes were detected by Felix Bloch. It was just after the Second World War. The World War ended and there were many military surpluses, so which means we had good magnets and radar technology. To use radars or these radio frequency equipment, they were heavily used by Bloch to eventually detect that how nuclear things behave with stars. So what we found is something like this. He took a box and put many spin of particles, any spin of particles, and put it in a magnetic field, and there will be Wheeler split. So which means that you have two energy levels with unequal population. More population at the bottom and less population at the top. So this is the picture that we are all familiar with. And the net result of this unequal population at two different energy levels is this collection of spins they acquire of magnetization. The big question is how does this magnetization behave? Meaning, suppose you have this magnetization and you apply an electromagnetic field on this magnetization. Then how do you expect it to behave? So that was straightforward. Classically, what we expect is dBdt of n should be this is what Felix Bloch expected, that this collection of polarization, meaning the magnetization, it should behave with the magnetic field using this law. This is from this we can get it from Maxwell's equation and with other supplementary parts. So for example, continuity equation. But to his surprise, he did this experiment, he took a collection M and applied some magnetic field, the M changed, and he could see that this equation they are following the solving. And then when he left it to relax, what he found is the magnetization is coming back to equilibrium. So which means, let's say you're talking about only the base component of the magnetization. Initially, suppose the magnetic field is also along the z direction. So this polarization, initial magnetization at t equal to 0 can be written as the initial magnetization along the z direction. So I mean, like essentially the polarization magnetization initially was along that direction. That's all. Now the equation of motion, if you use this cross product and suppose you are applying this b field along the x direction, suppose you have done that. In that case, you would expect the, I will write down the equation to show you how it behaves. This omega 1 is basically a measure of gamma times gamma is the dynamization and b is the sleep. Of course, we have to be on resonant and it should be time dependent, but leaving all this minor aspect aside, this cross product, the simple equation, Felix Bloch found that they actually match nicely with the experiment. Except when you speak of omega 1, they behave very differently, they come back here. But that means that you have to have a certain stars like the celebrated Bloch equation. That too some of you are familiar. So what block equation tells us is if you have monetization present in a collection and you let it evolve, then there are two processes which are competing against each other. One is the process which is shown in the middle segment, which is omega 1 my and omega 1 my. These terms are given by the external magnetic field that you apply. And the outer term, these are called relaxation terms. So these relaxation terms ensure that eventually, if you stop omega 1, the system will go back to thermal equilibrium. Just look at that. Look at the second equation. ddt of mx is equal to minus mx by dt. If you solve it at t equal to infinity, you know the mx will be 0. And similarly, in the presence of omega 1 0, if y at t equal to infinity will also be 0. So that means there is no transfer magnetization. And also, for the longitudinal magnetization, Lz will continue to grow or decay until it is equal to M naught. If it is equal to M naught, then this term is 0, and if omega 1 is also 0, the system will go back to equilibrium, the evolution will stop. So this is the classic case of non-equilibrium dynamics that we found. That was the initial situation that Felix Bloch found, that the polarization evolved, polarization evolved, and they also relaxed. The big question was, how do we explain that this origin of this term, origin of this relaxation term? This is the question that Felix Bloch and Alfred Redfield, they tried to answer that initially. What happens actually, if you look at this, my description, what I say, this is essentially in the sense that the Bloch theoretically found if we expected this work to hold, which happened, but this entire description initially he found this phenomenon in the sense that Felix Bloch did an experiment, he found this behavior, this is the behavior, and then he tried to come up with a scheme. The big question is, when the system goes back to equilibrium, then there has to be some kind of temperature involved somewhere. Look at this. I said that there is a given splitting and the lower level is populated more than the upper level. But that happens typically when the system has a temperature. Now we have a collection of streams in the box. How do they get temperature? The Bloch's idea was that they must be connected to the surrounding. This surrounding is unaffected by the magnetic field, and this surrounding he maintained during its at a particular temperature. So his idea was that at this temperature, I maintain the thermal bath, and the streams are moving in the bath. So no matter what I do with the stream, if I let them be, after enough time, they will come back to equilibrium, and they will inherit the temperature from the thermal bath. So he said, okay, fine, then let us develop a theory where we have a quantum system connected to a thermal bath, and let's write down the equation of motion, and let's see, how it works. That was the beginning of second quantum system. If you try to look at the history, some of the earliest important literature, 1953, Weierstrass and Bloch in physical review. It's a beautiful paper where the first time what he described Felix Bloch that if you have a quantum system connected to a larger quantum system, a thermal box essentially, then how does the equation look like? So he gave a tentative equation and he shows these equations, when you take the expectation value of observable, it looks exactly like that. So he validated his experimental findings for which he gets experimental equation, Bloch equation, by using solid quantum mechanical arguments. Sometime process later, Alfred Shakespeare came up with a beautiful theory which basically augmented Bloch's concept a little bit more robustly. And he actually showed that there is an alternate description of open quantum system also. I'd like to tell you very briefly both of them before I move on to the next part. First, the Bloch's part. What Bloch believes is extremely simple. He took a quantum system, a very simple spin half particle. And then he said that how do I model uh, a box? A box means what? Box is basically a thermal box that experimentally oftentimes what we do is we get a running water jacket maintained at a particular temperature and anything which connects to the water jacket, small quantity, for example, a small piece of metal or a thermometer, which have negligible heat capacity compared to the water jacket, then the heat lost from the jacket to this small piece of metal or the thermometer is kind of negligible. So that means the water jacket hardly changes its temperature. So block said, okay, fine, I will also kind of model it the same way that the thermal box must have very large number of energy levels with a lot of population. And this is a quantum system which is tiny. So if it takes a little bit of energy away from the thermal box, that will not change the kind of density matrix of the thermal box. Even the assume the density matrix does not change. The density matrix of the thermal box characterized by a particular temperature, and this temperature is not changing because of small energy changes. So that was his and how do we do that mathematics? That too was straightforward. He wrote the Hamiltonian in a simple way. This is the spin hot particle Hamiltonian, and this is the Bose Hamiltonian, and then this is the system bus coupling. Now, how does a system bus coupling typically look like? There are many ways one can model. First, we need to understand how does the box look like. I mean, I said many energy levels, but how do I exactly write it? A very popular choice, it happened much later, shown by Leggett much later, that uh, the box can be very successfully modeled by a collection of harmonic oscillators. So basically, instead of infinite number of energy levels of a single object, you can assume that your quantum system is talking to many harmonic oscillators. Each harmonic oscillator has infinite number of energy levels, and they can have different frequencies. So that would be a good model of. So this is basically the set of harmonic oscillators, and this coupling, you can think of it like a simple field magnetization coupling. So spin of particles will have some magnetization tiny and the standard Hamiltonian is you calculate the energy minus m dot b. This b is coming from the Bose Hamiltonian. So we mean this m dot, the b part must be connected to the polarization of the box. Temporarily, box does not have net polarization, but it can have a temporarily small polarization created. So it must have, how do I say, the harmonic oscillator, if I call it A, this, it must be of this form, m dot A kind of equation, where A is the polarization of the harmonic oscillator x, y, or z direction. So he assumed simpler form like this. Of course, I mean, much later we have James and Cummings who gave it a little more robust structure. They said that instead of a generic coupling between the magnetization and the harmonic oscillator, you can just choose a single spin of particles, put it in a cavity, and then the resulting Hamiltonian, which is somewhat like system of coupling, can be given as in its James-Cummings form. So what you have essentially is this is the harmonic oscillator raising operator, and this is sigma minus is the lowering operator for the system, and this is the harmonic oscillator lowering operator, and this is the raising operator of the spin. So essentially, you have a spin system and you have harmonic oscillator in your space. So you have flip-flop kind of variation. When A means goes up, the harmonic oscillator goes up, low energy to high energy. It captures a photon which is coming from a downward condition from the system, up to down. And the other term is just the Hamiltonian conjugate, which gives you the flip-flop kind of behavior. Now, I said that many harmonic oscillators would be required to model the Hall. So it means you do not use a simple AGV, you use many harmonic oscillators, and for calculating A equals B, you have to put sum over all such harmonic oscillators. It's a matter of detail. It's complicated, but this is a viable description. So that was the starting point from Bloch. At Bloch's time, we did not have the harmonic oscillator. We used the generic form. But much later, nowadays, we mostly use James-Cummings form to come up with the system of something specifics. The next part is just Bloch and Rossetti use, I can again write down the full Hamiltonian. Next step, what they do is, they go to interaction and representation with respect to the system and mass Hamiltonian, so that the only system of coupling remains, and then they do a time-dependent part of it. So somewhat like, suppose we begin with von Neumann-Liouville equation written in the angular frequency unit, the interaction representation. This is your equation looks like when you are in the interaction representation, and then you quadratically expand it in integrated form, and then in place of rho t prime, you substitute this equation once more to the same. There is a double commutator. The first commutator is HHG I means interaction representation at t prime with rho t, and the second one is the double commutator between two equations. And then the next step is you bring the rho t, this one, to the left side, divide everything by delta t, and what you get is, let me write it again clearly. I know I'm pouring in this sort of calculation, but this is essential in the development and of After that, if you at least if you do not get enough time for showing the slides, I will be able to give you some idea about at least how the dissipative nature in the quantum mechanics comes from. So please bear with me just a little longer. This equation, I will go back again. So you start from one normal linear equation, you integrate it. After the integration, you iteratively expand it using Picard's method. So this rho has been substituted by rho t minus, again, this is the integration of the one normal linear. After you do it twice, doing everything which do not have integration on the left hand side, and then what you see is the left side looks like a finite difference, and you call it a force ring derivative. This is a force ring derivative. Maybe you can put a force ring name to designate. Here, you see in the first term, on the right hand side, the density matrix is a function of time, but this is at t, lower limit of the integration. But the Hamiltonian is t prime. So which means if the system of Hamiltonian is time dependent, then the time average of the system of Hamiltonian will give you zero value in the sense if it is oscillating too fast, then on an average, the net oscillation, the net contribution from this equals to t time will be zero. So this is why we do not oftentimes get much contribution from the first order. And the second order gives you a net decay. I'm not showing you all the details. A little bit of calculation eventually gives you this double integral can be reduced to a single integral, and a little bit of change of variable. Essentially, what you have is that's it. This is the equation. You see, you have a time correlation of the system of interaction. So, if you at this stage, this is where the path of Redfield and Bloch diverge. But the common point was the next step is you take a partial trace over path. If you do that, then the equation of motion will be a simple system density matrix, equation of motion of system density matrix, because mass part has been traced out, and you are taking the trace over mass. Yeah. Right. At least some application would be good. Otherwise, it seems like, I mean, maybe it's disconnected completely. I do not hear much from your side. So I'd like to just add one more point, and before that, how much time I have? particular equation rather than the equation was not just suitable. If you remember, we started from this equation. This is completely unitary. It's completely unitary in the sense, look at this equation, there is a commutator on the right hand side, and the left hand side is time dependent. And how do I know, I mean, like, this equation is just Schrodinger equation, essentially. There is no dissipative component. And this does not give any dissipation. Then from this equation, we just did a partition one time, meaning I was substituted the integrated form of this equation twice, and suddenly the dissipation came up. What is the magic? The magic is here in quantum mechanics, the way we handle the working quantum system is the loss of information which is connected to dissipation. It comes from our lack of knowledge of certain degrees of freedom. In this case, this is the degree of freedom of the box. Remember, we are taking a space over box, and this Hamiltonian has system box. This is also system box. And this density matrix has system box as well as box part. The density matrix has been, it is two approximations. One is the Markov, the other is the Born approximation. For the Markov approximation, we assume that there is no memory, and for the Born approximation, we just assume the density matrix can be split at any time between the system part and the box part. Which means that there is no entanglement between the system and the box. This is an assumption. Whether it works or not, that will be validated by we take this equation and apply this on an experiment, and if it explains the experiment well, then we say that at least for that experiment, the Markov approximation is well justified. So this is our possibility. Of course, the way I have written, there are much more sophisticated way of writing this, but this is probably the simplest way of getting up to this equation. Now, so again, I repeat, the dissipation that you see is connected to our lack of knowledge about the box part. We are taking the partial trace over box, which means we are ignoring how the partial values are evolving. Moreover, we are making drastic assumption that despite having system and box coupling, the box density matrix does not change, and box density matrix is given to same as the equilibrium box density. I did not mention that previously. During Born approximation, we split the density matrix into two parts, system and the box. The box part, we assume that it is always fixed at the thermal equilibrium. That is enough. And if you do further mathematics, it's from now on, it's essentially mathematics. The important part of the physics that is needed to get the dissipation, there were three important parts. The part one was Markov approximation, then Born approximation, and the third was taking the partial phase in this partial phase. This was important. These three operations make sure that we are getting essentially the dissipative patterns. Now, if you thoroughly study open quantum systems, you will learn there are other ways of deriving this quantum oscillation. This is called quantum oscillation. There are many ways to derive this, and there are many sophisticated versions of quantum oscillation. Sophisticated version in the sense they don't look like this. It looks like much more usable handy form. And I would like to show you our group in math in Liverpool Professor. We have introduced a simpler form of quantum oscillation, which is very useful, and it does not require Markov approximation, but we do need Born approximation. I would like to show you that equation and a simple example of that equation. So with that, I stop here, meaning leave this part and switch back to my slide. If you have questions, please feel free to ask anytime. You can stop me and ask question or just type in the chat box. Now we are back here. I would like to here I would like to show you two things. One is explanation of a very important experiment that we could not provide it before using a master equation that our group from our Russell brother we have proposed. First I describe the experiment. This is a collection of spin-up particles and they are dipolar coupled. So each spin-up particle talks to the other spin-up particle. Then what you do is you flip them. So initially they are in the z direction, which is the up along the up in the slide. And you see the horizontal arrows, they will indicate all the spins are in the x direction. So you flip them from z to x. Then you lock, apply a drive which is also along the x direction. If you do that, then what happens is the magnetization decays very slowly. It almost does not decay. It stays there as long as the drive is on. And after a very long time, it reaches the thermal. If you look at the density matrix, initially when you think the density matrix contains the single quantum curve is shown by the card colors, the clubs and states. And then after a certain time, it develops entanglement as well as single quantum curves still further. And after a very long time, it's nearly died. So it's almost a thermal cell. The big question, the problem is, if you do not apply the drive, then it decays very quickly. The density matrix becomes diagonal very fast. The moment you apply a drive, the whole thing, the decay is arrested. The decay becomes very slow. It's a puzzle that could not be explained using the quantum of equation until very recently. So here is an experiment where people did this and validated experimentally. I'm just skipping over it because we already mentioned what it is. Now, our next equation, the way we do it is this. Quantum systems, they interact with local environment, and we assume that the local environment, they undergo fluctuation. So we make a model where the energy level of the environment fluctuates about some mean value. And these fluctuations destroy the coherences in the environmental part. So the coherences in the part. So essentially the Hamiltonian looks like system plus the environment, which is the part. I mean, in the slide, whenever you see environment, you can translate that to part. And that will be exactly fine. Then we have the APSB term, which is this interaction. And there may be a drive term also, meaning we are applying a drive just like Phillips law gauge of the system. So this is captured by a Hamiltonian interpretation. This bold curve is our addition. We believe that even a thermal bath must have spontaneous fluctuation of the energy level. So this is embodied by the term Asia. Then what we do is we construct the propagator. We take Schrodinger equation in the propagator form and expand it. This is the expansion. So E T1T is basically identity minus T2T1 dt2 Hamiltonian times U. Because you remember the Schrodinger equation is rate of change of U is equal to minus IHU. It's simply the integrated form of that. Except the Hamiltonian has been split into two. One is the effective part, the other is the fluctuation part. Then what we do is we take the last part, the fluctuation and the identity part, club them together, and what we have is evolution only under fluctuation, UL. And another term integrated system Hamiltonian, it contains drive and the system interaction, system environment interaction, times the evolution due to the fluctuation. So this is a hybrid type of propagation which captures infinitesimal propagation under system Hamiltonian and finite propagation under the Hopf Hamiltonian. If you use this propagator and continue with the standard form of getting the quantum of the equation, this is what you have. As I mentioned, there are other ways of writing this. So this is our way of writing the quantum of the equation. That we have the drive and the dipole part of the Hamiltonian acting on the density matrix in the first order. There is no crystal environment coupling in the first order. And we have dissipator which is coming from drive, coming from dipole, and the crystal environment coupling, and it's acting on the density matrix. So this is our new equation, which basically describes the open quantum system. Here is an experimental verification of this one, which I would like to skip for now. I would like to come back to the model where we just take two schemes, put the dipolar coupling, apply a drive of the x direction, Wheeler field is acting on the z direction, and system of coupling is, as I said, it's basically collection of harmonic oscillators connected to these systems. Its total collection. The B terms are harmonic oscillator raising and lowering of frequency. Then what we do is we go to the Lewis space and the equation looks extremely simple that rho s dot equal to L rho h. This is rho s dot in the Lewis space. The density matrix is column. So it's basically rate of change of the column vector is equal to matrix times another column vector, the same column vector. And this can be easily understood by diagonalizing and looking at the energy eigenvalue of the Lewisian. The Lewisian has this property, energy eigenvalues are, they have a real part is always negative. They may have imaginary part, and none of them are positive. So this guarantees that the density matrix has always a decaying solution, it does not divert or blow up. So once we take this density matrix, this equation, and we use our Maxwell equation, this is the description that we get. So initially, your schemes are split. After splitting, they evolve, and then they stay considerable amount of time without decaying, they stay locked, and eventually they go to a thermal band. So what you see remarkably here, previously, in the previous situation, one, it was not possible to explain why we are getting a plateau-like region. This plateau-like region is actually explains lot of things, including the very recent experiment on discrete time crystals and others. But this black region essentially the signature of the presence of the dissipator coming from the drive and the dipole. Our Maxwell equation predicts that, and experimentally it has been verified. The experimental data, I would like to show you this data, this particular box at the right corner. Look at it. Initial oscillation, then it's kind of flat, non-decaying, and then it goes to thermal balance. And look at our prediction. It's same. We did not show the oscillation to make the curve simple. Initially, ours also oscillates, and then it goes there, then it slowly decays, and eventually goes to the thermal balance. So these cascaded dynamics can have multiple plateaus. This is another prediction which is looking at, people are looking at experimentally also, they are taking it out. That initial transient will be there, oscillation, then there will be a thermal plateau, then a constant dynamics, a second plateau, and unconstant dynamics will be final form. So this is basically, it tells us eventually very important result that a quantum system can have multiple stages of evolution. It does not go to equilibrium smoothly. It may not go to equilibrium smoothly. It can go to a particular state, what's equilibrium kind of state, and there it can stay locked for some time. Eventually it goes away from there and can go to a second quasi equilibrium, and eventually it can go to thermal state. So it can have a cascaded dynamic. Now, I'd like to stop here. I think I will be taking more than an hour. It's quite long time. So this is our good in lab at either professor. And the essential summary is this power master equation effectively. It explains temporal evolution and it explains the two kernel plateau. And the constant normalization happens due to non-secular diagonal. So we have something I did not explain, so let's ignore that. We, for you, the what I said, I mean, I think the summary should be, let me go back to, yes. The summary should be, first of all, open quantum systems are quantum systems connected to environment. The environment is modeled as a thermal bomb. So you have to write Hamiltonian for the system, for the thermal bar and their interaction. Then you do a quaternion theory. There are many ways of doing that. I showed you one example. Using that quaternating approach, what you get is a double commutator. It gives you dissipation in your equation. The essential source of the dissipation is not just the double commutator, but because we take a partial phase over the mass. This partial phase over the path is crucial. And this also guarantees the system goes back to equilibrium and it takes the temperature from the path. Now this description is entirely mathematical, but it works very well. It explains experimental results very nicely. And as for our group, we propose a variation of quantum master equation. We use that quantum master equation to show that at least the spin locking behavior, that the spins are flipped and locked. These could not be explained for open quantum systems, but we have an explanation for that. And this cascade that you can still see, this is one of our recent results on open quantum systems. And with that, I stop here. Thank you very much for bearing with me. I mean, I could not see you. I hope that you enjoyed. I wish that I could come there and physically give the lecture. Would have been very nice. To see you in front of. I mean, like, to have an interaction face to face. Okay. Thank you. Thank you very much. I stop here.
Thank you, Professor Bhattacharya. If anyone have any question, please let us know. We will convey to him. Then he will answer surely.
If you have questions, please let me know.
Question answer পরে কন্ট্যাক্ট এখন কোশ্চেনগুলো পরে কন্ট্যাক্ট করে মুখে বলো মুখে বলো
I'm not taking anything from your end. I mean, you saying something? No. Okay. I take down my presentation. You can continue. I think that would be nice. Would be nice. I mean, see, if possible, I would be very happy to visit presidency. And that will not happen now, I mean, because of my physical condition. It can happen later, maybe in January, maybe it starts again. And I would be very happy to interact. I mean, and question and answer, you can ask me anytime. My email, you know, romita@idapolicy.in. You can send me mails also. I mean, whichever way, just reach out to me. I'll respond as quickly as possible. I thank you once more. It was really a pleasure to me to give the talk. Thank you.
So thank you, Professor Bhattacharya. And
কি লাগবে?
Okay, now we'll move to our next session for this question.
Okay. Yes. You are asking Streamlab website. Just search my name from the Bhattacharya, you will get a Streamlab website. Maybe I'll write it. Just type it here.
সিস্টেম করা।
This is the website, Streamlab website. It's not very updated, but you should be able to see that. Me and our research area, we work on